Hello, everybody. So as announced, there will be a quiz next week on Thursday, starting 4 o'clock. Okay, so before that, we'll also have the homework number 3. Okay, so I will post it this week sometime, which will be due before the exam. So maybe on Tuesday or something, or Monday. So guys, any questions so far? Okay. Any questions so far, guys? Okay, so let's go to tutorial problems. We will solve a few. Okay, so let's just a minute. Okay, so let's look at, so first question is 4.3. Okay, there's a lot of questions. Okay, I mean, you have to actually do it. So what I will go through is just the process. Okay, how you do it. So question number 3 is show that the time Tp corresponding to the peak response of a damped, okay, just a minute. So this is 4.3 only. So Tp, you have to show that this is for the peak response of a damped spring mass system. So a spring mass system, so Kc like this. Okay, excited by a step force. So a step force is this, and because of that, there will be a response which will go like this, as you know now. And you have to show that if Tp is the peak response, so here this is Tp, where the maximum response is the time t equal to Tp. So you have to show that omega n is natural frequencies, Tp is equal to pi over root 1 minus theta square. So this you have to show. Okay. So how will you do it? So you have to write the equation. Yeah, you have to start with the equation, and there will be a step input force. So this is the force here, which is a step input F naught. So you can, you know how to solve it, and solving it, first you write the equation, and for this equation is mx double dot plus cx dot plus kx equal to F. But in this case, if it is a step input, this will be F naught, right? And then you are going to take the best thing is to take the Laplace transform. This is the, so transient condition you can solve this very easily. So we go and we find out what we find out. This we are assuming this is starting from the what are we assuming? Assuming x 0 equal to 0, x dot 0 equal to 0. From there you are going to apply the force, right? Okay, now so you have what? mx double dot plus cx dot plus kx equal to f naught. You applied the Laplace transform, and what do you get? You get, before doing that, we can have divided by m here, divided by m here, divided by m here. Okay, so that you have, accordingly, we will have xs plus 2, here it will be s square, yeah, 2 zeta omega n, and then you have s x s plus, here you have omega n square, okay, and then xs, which is equal to f naught over m, right, equal to f naught over m. Okay, and we have remember that this is a constant. So when we take a constant of like any constant, then we have 1 over s this side. Yeah, so Laplace transform of any unit step function is nothing but 1 over s. So hence we have 1 over s value here. Yeah, and accordingly we can find out xs is equal to, and then we have f over m times s divided by s square 2 zeta omega n plus omega n square, right? And then we take the Laplace like inverse Laplace transform, so we get xt, which is inverse Laplace transform of the whole thing. Now you follow your lecture, okay, to do inverse Laplace transform of this one. So this becomes f naught. Yeah, so here what you get is f naught divided by m s, and then you have 1 over s square plus 2 zeta omega n s plus, then you have omega n square. Okay, so you do all the simplifications required for this, and then you find out what the value of xt. Okay, so the value of xt you can find out. What will you find is, after you have done the inverse Laplace transform, your value looks like something like this. So it goes like this. It goes like this and like this. Okay. Now where the peak is, which is Tp. So that we have to find out. And how will you find out? Now what you have to do is, this is the first place where you will get slope here, right? So this is the slopes, and hence the value will be right there, the velocity will be 0. Yeah, so dx over dt has to be 0 where x is not equal to 0. Yeah, so you have started x equal to 0, x dot equal to 0 from here, so other than this one. So but there will be many such points, this point, and so on. We are looking for the smallest one. Yeah, I mean smallest Tp. Yeah, this one. Okay, so by doing this analysis, we can find out, this will give you the Tp value. Yeah, so automatically you can this relationship you can find out from there. This. Okay, so automatically we will see that here pi is there. You will have n will be here. So n equal to 0 either it will be, or n equal to 1, so you get pi, and so on. So n is equal to 1, you get this value, and hence this is, yeah, because you will have sinusoidal function in the x, sinusoidal term will be there. So as I said earlier, so I assume you are able to do inverse Laplace transform from here, and this has been done many times in the lectures also. So any question, guys? Okay. So if you have done this one, 4,4 you can do immediately. So 4,4 is related to this one only. And what does 4,4 says? This says that for the system in problem 4.3, show that the peak response is equal to, yeah. So peak response basically x will be x at Tp basically, right? And you can find out in that case this will be the value will be equal to this one, f naught divided by k and 1 plus e minus xi pi divided by 1 minus it. So what we are doing, just we are putting value of Tp where we get an expression for x, and in that we are putting a value of Tp, and Tp value you are getting from earlier. So Tp is equal to pi over omega n root 1 minus eta square. So we get expression of x from inverse Laplace transform, and then your derivative you are taking, and if you take the derivative, then what do you get? You get x equal to you will get some value of x, and there it will have sinusoidal functions. So to make it 0, it will has to be sine. So it will be something like this: sine n pi and some other term is equal to 0. So n equal to 0, n equal to 1, and so on. So n equal to 1 will give you the maximum one, and hence you get the Tp. Once you get Tp, then you put in x, t equal to Tp, you get the maximum displacement. That's what you are doing. Yeah, so you can do this way. So anyway, so these are answers are given already. You just have to work out, or hence I'm leaving this on you. Okay. Now let us see. Okay. So let's look at question number 4.6. Again, this is okay. I'm leaving it on you. So you have to show. So do yourself, because here again this is the solution is given. So you have to show that this is do yourself. So this is like a proving how to prove it. So you can do it. Okay. Now 4.7, show that the response to a unit step function designated by Gt is related to the impulsive response Ht by equation Ht equal to Gt. Okay. Okay. So let us say you have 4.7. Show that the response of a unit step function designated by Gt is related to, so let us say our equation is mx double dot, yeah, and plus cx dot plus kx equal to f, right? This is the ft. So we have a spring mass damper system, yeah, so this could, and then we have the force function f. Now it says that the response due to the unit step. So unit step, then in first case, what it is saying that the response is given by Gt. So now let's assume unit step function. It's a unit step function. Okay, so ft is unit step function, so ut, that really means, yeah, and then if we take the Laplace transform, then what we get? So Laplace transform of mx double dot plus cx dot plus kx, and unit step function Laplace of unit step function ut. And what do you get? You get ms square. Here we are assuming we are starting from 0, 0 in that case, and then c s plus k at times xs equal to unit step function, so it gives 1 over s. And then it tells you that xs is equal to 1 over s. So 1 over s, then we have ms square plus cs plus k. Okay, now this says that the response due to unit step function designated as gt. So this is what the gs is. Okay, so it's given since gt equal to xt. Yeah, for f equal to ut is given. Yeah. Okay. Now this is given. Now second thing is second condition. So this is case 1 where we are calculating. So this is case 1. Case 1 is for ft equal to ut. Okay. Now case 2. Okay. Case 2 is okay. So case 2 is impulsive response. Okay. So what do we have? We have same equation, mx double dot plus cx dot plus kx dot is equal to one impulse response. So we have something like this, delta t. Right? So this impulse response, unit impulse response. So unit impulse response, not response, but unit impulse force. Yeah. Okay. If that is the case, then if you apply the Laplace transform, then what happens? You get ms square plus cs plus k, and then xs. Okay, and this is equal to 1 because Laplace transform of the impulse force will be equal to 1, and hence you get like that. Yeah, and hence in this case, what do you get? You get xs is equal to 1 over ms square plus cs plus 1. And this is equal to what you call it in this case hs. Why? Because ht equal to ut with force F equal to delta t. Yeah. So if you compare this, let's say this equation number 2, and compare it with the previous one. So this is equation number 1. So what do we get? We get gs times s equal to, so we get like this. gs times s is equal to hs. Yeah. Okay. Okay. If that is the case, then if we take Laplace transform now, okay, so we take inverse Laplace transform now. So we have this one, and then we take inverse Laplace transforms of gs times s is equal to inverse Laplace transform of hs. And what do we get? From that we get, this becomes g dot t, because s times gs in inverse Laplace transform is g dot t basically, right? So this is g dot t is equal to ht. Yeah, so this is what you had to prove basically. Yeah, this one. So you got that. Okay. Any question, guys, so far? Okay. Let's look at 410. An undamped spring mass system. Undamped. Okay. So we have mx double dot plus kx. System is given a base excitation. Okay. So first we have to look at the base excitation. So we have this like this. So we have m here, we have k, this is base. Yeah. So we have y here and we have x here. Yeah. Okay. So first we have to find out the equation. The equation will be something like, so let's not write this one. So let's say x is let's say y is greater than x. Okay, so that way easier to visualize. So what we see is m, and then this has gone up. Because of that, this is a compression. So because of that, there will be a force applied here. Okay, and what will be the force? Force will be distance between this and this. So the force will be k times y minus x. Okay, so why? Because y is greater than x, and there will be a compressive. When you have compressive force, in that case, the force will, the spring will apply force upward, and hence you have the force like this one. Yeah. Okay, and then this value has to be equal to, so k y minus x has to be equal to mx double dot. Right? This is Newton's second law. And because of that, what you get is mx double dot plus kx equal to ky. So this is the equation you get. Yeah. Okay. Now what it says the coming back to the question, it says it has base excitation of, so given. So this is the equation, governing equation. What is given is y dot t is equal to 20 1 minus 5t. Yeah. Okay. So let's say this is equation number 1. This is 2. Right. So from 1, so Laplace transform we can apply from 1. And we get mx double dot plus kx equal to y, ky, sorry. Okay, and then you get m s square xs plus k xs is equal to k ys. Okay, so this is equation number 3. Now from 2, okay, from 2 y dot, so we take Laplace transform of that. So y dot t is equal to 20 1 minus 5t. Okay, and what do we get? We get, in this case, s y s. Okay, assuming y is 0 at equal to 0 is equal to 20, and then we have 1 here. So for 1 we get 1 over s minus 5. For t we get 1 over s square. Right? So we get ys is equal to 20 over s 1 over s minus 5 over s square. Right? So this we get. So equation becomes 20 ys equal to 20 over s square. Okay, 20 over s square 1 minus 5s. Okay. Okay, so this is equation number 4, we can say. This is 4, and this will put in equation number equation number 3. Okay, so then what do you get? You get ms square. So we get xs. So put it in equation number 3, and you get ms square plus ca, sorry, not cs. So we have this. So ms square plus k. So not cs. ms square plus k multiplied by xs is equal to, and then we have kys. So we get k times 20 over s square 1 minus 5 over s. Yeah. Okay, and then we get xs. So xs equals also, we have to find out, natural frequency of system omega n is given, determine the maximum relative displacement. So we have to find out xs basically. So we have to find out xs is equal to 20 k over s square 1 minus 5 over s and 1 over ms square over k. So this is what we get. Okay, so xt you can find by, so xt Laplace transform, inverse Laplace transforms, and then 20k. So 20k over s square 1 minus 5s, 1 minus 5 divided by s, and 1 over ms square plus k, 1 over ms square over k. Okay, so this is how you find out xt, and then accordingly in the case whatever value you get from there, you can find out the maximum value. So once you know this one, you can even plot, and you can find out what is the maximum displacement you can get. But rest you can do yourself. You have to simplify this one, and then you can find out what is the value of xt. Yeah. Any questions so far, guys? So no question at all, no doubts. Okay, now let's look at 13, 14. 13. Okay, so now for 13. So here we have arrangement like this one. So there is a slider, goes like this, and like this one, and there is a mass m which is coming like this one. Distance is s, like this. Okay, and this is 30 degree. So let's say distance is d. Okay, so distance dy, because we use s as the complex frequency s. So here we have like this. This is k. Now a string mass system slides down a smooth 30 degree inclined plane as shown in figure determine the time elapsed from first contact of the spring until it breaks down again. It breaks the contact again. So what it will do, this will slide down. So this is sliding like this. So this will come, the spring will touch here, they will compress and then go back. Yeah. So accordingly, we have to find out what is the time required and all. Okay, so how to solve it? So first thing is, from here we have to find out what is the velocity when it is making the contact. Yeah. So in such questions you have to look at, you can look at the where exactly it is coming. You can also use the energy methods. Basically for that also you can use, but here it is complicated, meaning that you will have the spring compression, then you have a gravity. Because of that you have to take take care of that, and then you also have the velocity is there, so kinetic energy will be there, then potential energy, because of this also have the gravity there, right? So gravity is also there, so it's complicated, but we can use differently also. So like just Newton's law we can apply, and based on that also you can do. So how? So first, for this system we have to look at first what is the velocity. So when it comes here, when it just touches this, so we have this kind of system, right? Okay, this is it. So this is just touching right now. So in that case, what is the velocity we have to find out. And remember that it started with this kind of system where you have the distance d, yeah, and in kind like this one, and from here we have to find out. It starts from the this is in rest right now, and it comes like this one, right? So if g is, we have to also look at the acceleration. So if g is like this one, yeah, so what will be the in g in this direction? So this is g here and a 30 degree here. So here this is a 60 degree. Yeah. So g here will be g cos 60 degree. Yeah. So g cos 60 degrees is equal to g over 2. Right. Okay. So what you have here in this case is acceleration is this way, and this is g over 2. This is the acceleration. Yeah, and it has traveled by d, distance d, so we can find out v equal to u plus at, but in this case we have s equal to s equal to v square equal to that we can use. So v square equal to u square plus 2as, and in this case s is nothing but d, and a is nothing but g over 2, u is 0. So what we get? We get v square equal to 2 times g over 2 times d, and v square equal to g times d simply. Yeah, or v equal to root gd. So you get v, or this is equal to x dot 0, that you get. Yeah. So x dot 0 we found out, which is equal to zd. Okay, and our x is in this direction. Remember our x. Okay, that we can define. So let's not define the direction of x yet. Okay, so x dot 0 is equal to this. Now next is when it goes and attaches, when a spring comes to contact of the wall, then since this is under gravity, so let us say if we just leave it like this one, meaning that this system is attached to here. Let us say if there were no velocity, we had just let it settle, then the equilibrium point will be equal to, so we can also say the equilibrium point in this case. And how to find out? So let us say here. So we have mass here, and then we have the spring here, like this one. Yeah. So it goes like this. And this is the actual, D is the, not D, but let us say the original length is L. And we have acceleration due to gravity in this direction with g by 2. So hence the force F will be equal to m times g over 2, or mg over 2 will be the force in this direction. So displacement, or x naught, let us say, so k times x naught will be equal to mg over 2 simply. So x naught will be the displacement. So so basically what I mean to say is, same problem we can now formulate as, there is a mass coming, and this is just spring just touching at the wall here, and right that time we have velocity. Which direction? This direction. V naught is equal to whatever we calculated here. So this is let's call V naught also. So this is V naught. Okay. So we have V naught, right? We have V naught, and also if you, the equilibrium position is somewhere here, where this distance from here to here is, from here we can find out this. So x naught equal to mg over 2k. So this is the distance mg over 2k. So why we did that? Because this is the equilibrium position. So at t equal to 0, so this defines t equal to 0 now. Yeah. So this is t equal to 0. At t equal to 0, we have velocity v naught, we have the position x naught is equal to this one. Now we have to see the sign basically. Depending on which side our x is, accordingly we can find out. So we can now have that our problem now changes to a spring mass system, right? Which has this is equal to equilibrium position, and then you have, let us say, x is this way. From here we are defining x this way, let us say. Then we have x naught. So that means we have x naught, or x0 equal to, given by mg over 2k, and x dot 0 is given by velocity which is in opposite direction. If our x, this is x is our displacement. So if x is this way, velocity is the other way. So x dot is equal to minus value we have found out earlier. So here root gd is equal to minus root gd. Yeah. Okay. So this is our finally this is our equation. We have to solve it. So which equation we have to solve? We have to solve this mx double dot plus kx equal to f, right? With what? With f is actually f is constant, and what is the f? F is being applied throughout. So the f remains. This is the f applied here, and this f is equal to mg over 2. So this is mg over 2. Okay, and this is our equation subject to x dot 0 is equal to velocity it is, which is minus root zd. So minus root zd, and x0 is equal to mg over 2k. And this, so from the physical system, we found out the mathematical system, and we have to find out this one. Okay, so we can now solve, we can find out the value, and we do the transform, we can apply here. Yeah, so we get of mx double dot plus kx equal to mg over 2, because this is the force it is being applied. And then what do you get? You get here m s square plus ks, right? And then you get xs is equal to mg over 2, then 1 over s. Or xs will be equal to mg over 2s, and then 1 over ms square. Okay, s will not be here, so okay, no s here. ms square plus k. Okay, and hence we can find out xt from there. So I'm leaving on you how do inverse Laplace transform to find out xt, and you get mg over 2s, and then 1 over ms square plus k, 1 over ms square plus k, like this. Yeah, so you can find out the value of xt, and once you have find out the value of xt, and then we can find out the further answer. The answer is determine the, so we have xt like this, determine the time elapsed from the first contact. So t equal to 0 is the first contact. Okay, so one thing guys, here we missed one thing. We have to, this is true only when this equal to 0 and this equal to 0. Okay, so this will is not correct. So let me correct it now. So no, this is not correct. So I forgot to apply that. So not this, this is incorrect. So the answer will be in this case will be ms square minus, okay, so here m s square x m square xs, okay, then we have minus x0 s minus x dot 0. Okay, so this will be m, okay, because x0, x at 0, sorry, because x at 0 and x dot at 0 is not equal to 0, hence we cannot neglect this one. Okay, so has to be there. Similarly, for second term, we have this. Yeah, so we get a k. So in this case, it will be direct plus k xs is equal to mg over 2 1 over s. mg over 2 1 over s. Yeah, and hence what we find in that case is ms square plus k multiplied by xs will be equal to mg over 2s plus m x0s plus x dot 0. mg over 2s plus m coming from here x naught s plus x dot 0. Yeah, done. Okay, and hence you can find out xs equal to divided by 2 becomes, so mg over 2s, so 1 over ms square plus k, then mg over 2s plus mx0s plus mx0s plus x dot 0. Yeah. Okay, and we can now apply inverse Laplace transform xt equal to L inverse xs. So this you know already from your mathematics class. So you can find out what the value of xt. Once you have that, now we have to find out the time elapsed from the first contact of the spring until it breaks contact again. So it will break contact when? So this our t equal to 0 is is when makes contact, right? Makes contact, and at that time, what do we have? We have xt x equal to, so we already have these values. So at that time, this is at t equal to 0, all right? T equal to 0. So x0 equal to mg over 2k. x0 mg over 2k. Yeah. So when it leaves the contact, that time, yeah, okay, so we also write x dot 0 equal to minus root zd. Yeah, okay. Now, t equal to, let's say call t equal to, the breaks the contact, t equal to tb, let us say, breaks the contact. So that time, what happens? Our x0 becomes again mg over 2k only. Yeah, and then what else you have? In that case, we will have so same position because of the arrangement. If you see the original one, so here, so this is just making the contact right now, and then mass will move here, and then it will start moving forward, and then it will comes back to the same position where it had just made contact, and after that it will leave, right? So it will actually have the same velocity. So this is coming with this velocity this way, and then it will come down, and then it will go with the same velocity but this direction. Yeah, so same velocity will maintain, it will come, and same velocity it will go at this position, it will have the same velocity that way. Okay, now so if t equal to tb is the time at which this breaks the contact, then x at t equal to tb, we will have again x0 equal to same value, right? So we will have if x0 equal to this one, this denotes that at x at tb will also equal to mg over 2k. Yeah. Okay. So this is what we have to do. We have to first find out xt. Once we have found out the xt, we put the value of tb, t equal to tb, and we make it that equal to mg over 2k, and we will find out the value of tb from there. So this will give the value of tb that way. Okay. So here I have we have gone through the process, basically how to solve this one. Actually, you have to solve them. Yeah, so this is I'm helping you. the main thing is writing the equation. So once you have written the equation, you can solve it. So any question, guys? Any question? Okay. Okay, so you have quiz next week on Thursday, as I announced, starting 4 o'clock. If you have any question about the quiz, let me know now. Okay, if there is no question, then see you guys next week. Okay, see you.